Right, hello everyone. My name is Valentin. I'm one of the committers of Apache Ignite project. And also I take a position of lead architect at GridGain systems. And my main focus and my main responsibility is working with our customers and our users and to help with their technical challenges. And therefore I see a lot of real use cases, and I see how Ignite and GridGain is used in the real world. And today I want to cover a topic which brings a lot of questions. So I think it's pretty important to go through these questions and through challenges that our users have regarding this topic. And this topic is how to build a distributed system which is both consistent and highly available at the same time. This can be quite a challenge. And obviously, I will go through all the features and techniques that are available in Apache Ignite and GridGain to achieve that. In more detail, here is the agenda for today, for today's talk. So I will start with a very short introduction about what Ignite and GridGain is. Then I will cover and I will talk about how Ignite and GridGain stand in the CAP theorem. And then I will go through all the features and not all the, but major techniques and major features that are available in Ignite and GridGain that allow to build distributed system that are consistent and highly available at the same time. And I will cover topics like cache backups, persistence, data center replication, and data snapshots. And I will also have a quick demo for data snapshots. And we will, of course, finish with a Q&A session at the end. All right, so first of all, how many of you are familiar with Ignite and know what it is? I hope many of you. Yeah, so my overview will be pretty quick, I think. That's the second day of the conference. So in short, it's an in-memory computing platform, which means that we do processing in memory and we store data in memory. But at the same time, it can be durable, and I will explain how. And it's also strongly consistent and highly available. And it provides multiple APIs like SQL, key-value APIs, different types of processing APIs, and so on and so forth. And that's how it looks like from more architectural perspective, right? So in the heart of the system, that's how your system built on top of Apache Ignite will look like. So at the heart of it, we have a memory-centric storage. I will also explain in more detail what it means. But basically, this is a data storage where you have your data. The data storage is primarily in memory, but it can be integrated with different types of persistent layers, including any type of third-party persistent storage, like relational database, HDFS, or whatever else. And we also have our own Ignite native persistence option. And then on top of it, we have different APIs that allow you to access this data storage and to work with the data in that storage. It includes SQL, key value, APIs, transactions, compute services, and so on. And on top of that, using these APIs, you build your own systems, right? And this can address different types of use cases. We have a lot of use cases in financial services. This also includes telecommunications, retail, travel, and many others. And on the side, this blue part is actually a GridGain part, which is not included in open source Apache Ignite. We provide several enterprise features on top of Ignite, such as data center replication, security capabilities, monitoring, management, and data snapshots. Okay, so the data storage that we have at the heart of our system works with data, and we have two major use cases that I'd like to outline. So the first one is the data grid. Data grid means that you have basically key-value storage, and you work with it primarily with distributed hash map, basically concurrent hash map. It's very scalable. You can dynamically scale it out by adding more nodes. It can be integrated with any kind of persistent storage, including third-party persistent storage as well, or native persistence as well. You can use JCache API to interact with the storage, and as well as using SQL queries to get more complicated searches on that data. And it's fully transactional and fully consistent. And the second one major use case is a distributed SQL database. In this use case, you use Ignite kind of as a SQL database. We have all capabilities to work with Ignite pretty much in the same way as you work with any relational database. So we have all the SQL capabilities, including DML support, which allows you to update the data using SQL language, and DDL support, which allows you to create and modify schema using SQL language. And we also provide JDBC and ODBC drivers, which means basically that you can access Ignite from any platform and from any application, and as well as generic JDBC, ODBC tools, or different BI tools. And of course, it's also dynamically scalable, fully consistent, in the same way as the data grid part. All right, so this was like an overview. So let's jump into the actual topic of this talk. So first of all, that's one of the biggest questions I get very frequently. So how GridGain stands in the CAP theorem? So just as a reminder, CAP theorem tells us that any distributed system has pretty much three major characteristics. First one is consistency, which means that if a system is consistent, it will never give you incorrect result. So whenever you request some piece of data from the system, it will give you the actual consistent value back and never anything else. The second one is availability, and if system is available, it means that you will never get an exception from the system. So it will always give you some result, right? And partition tolerance, which means that basically system can survive network partitions. And basically the theorem claims that you cannot have all three characteristics at the same time in one system. So it can be consistent, available, and partition tolerant at the same time. And the most common interpretation of that is basically that there is a trade-off between consistency and availability, which makes sense, because if you think about it, partitions will always happen. It's not something we can avoid in a distributed system. And therefore, partition tolerance is a must for a distributed system. And then you can have both. You can have both consistency and availability, because if something bad happens that breaks your data, you basically have a choice. You can either return incorrect result for request for this broken data, or you can give an error, saying that I can't give you this data. The first one will mean that system is inconsistent. The second one will mean that system is not fully available. So the most distributed systems are either CP or AP. Some of them are neither of them, but anyway. But there are no systems that are CAP at the same time, right? And as for GridGain, it's a strongly CP system. It's a strongly consistent system. So GridGain will never give you incorrect result when you request the data. Well, strictly speaking, it can be both AP and CP, depending on how you configure it. But I will focus more on CP scenario because it's much more challenging. So GridGain is CP system. So what it means? It basically means that it's not fully available. It's not available 100% of the time. But for most mission-critical system, that's very important that system is available at least most of the time. And Ignite and GridGain provides different techniques and different features that can increase the availability of the system. So it will never be 100%, but you can make sure it's like 99.959 after the dot, something like that, right? And that's what you're looking for, basically. And I want to talk about how you can achieve this with Ignite and how to increase availability of the system. All right, so let's start with the basic technique and a basic thing that allow you to increase availability. These are cache backups. This is a very simple thing, right? So let's start with a very simple scenario. We have a 4-node cluster without any data. So if you create a cache on Ignite, a distributed partition cache on Ignite, and put some data in it, you will get something like this. So the data will be distributed across the cluster. So every node will get its own portion of the data. And in this scenario, so this is like the default behavior. By default, there are no backups. That's how it will look like. So let's imagine that one of the nodes is down. So what will happen in this case? In this case, we basically just lose this portion of data B, partition B. And if a client tries to access this something in this portion of data B, it will get an exception, which means that the system is unavailable at this point, right? So to solve this problem, we do a simple thing. We just configure to have one backup on this cache. Having a backup means that for every entry in the cache, we will have another copy. So it will look something like this. So there will be a second copy of every piece of data somewhere else in the cluster. And in this case, if I kill the same exact node, you can notice that we have all 4 pieces of data somewhere in the cluster. We have A here, B here, C, and D here, right? So we did not lose anything, which means that the system is fully consistent, and it remains available regardless of the fact that we just had a node loss. Okay, but what if we actually lose one more node at the same time, right? We obviously have the same problem. We lost the same partition B because it does not exist anywhere on these 2 nodes. We have only A, C, and D. Again, system is unavailable, system is not consistent. So how do we solve this problem? Does anyone know? Exactly, we add one more backup. Here we go. So it will look something like this. Again, if you configure a cache to have 2 backups, it will just mean that you have 3 copies of the data of each entry somewhere in the cluster. In this case, if I kill these 2 nodes, I have partition A, partition B, partition C, partition D available on remaining 2 nodes. So we increase the availability of the system even more. And you can go further and add more backups. And you can reach the extreme case when you have actually backups on every node, which creates a fully replicated cache. So what it all means, it actually means that there is another trade-off between availability and scalability. Because from availability standpoint, looks like nothing is better than a replicated cache, right? You can afford losing all nodes except one, and system will remain consistent and available. But this approach is obviously not very scalable, because if you have very large data set which does not fit in a single node, you want to be this data set distributed across the nodes. All right, let's take a look at a bit more complicated example. Again, we have 4 nodes. We have a distributed cache with one backup, with some random distribution across nodes. But in this case, nodes are deployed on different racks of servers, or maybe availability zones on the cloud, or whatever, right? So basically, 2 nodes on the first rack, and client accesses this node through the switch, and the same happens here. And let's imagine that we lose not a single node, but we lose the whole switch, and basically the whole rack of nodes, and all the data on this rack of nodes is gone. So what happens in this case? We again have a problem, because we don't have a partition A here. We have B, we have C, we have D, but we don't have A. So partition A is lost, which makes our system unavailable and inconsistent. And you will get an exception when you try to get something from this partition A. So Ignite has a pretty nice technique to solve this problem. It is called Affinity backup filter, which you can configure on any of your caches. So basically, there are 2 steps to solve this problem. The first one, you assign a special attribute to every node in the cluster. And this attribute kind of identifies on which rack it's running on. So if it's running on the first rack, for example, it will have this rack 1 as a value. For a second rack, you will have rack 2, and so on and so forth. So this will become just a part of the configuration of the node. And then, as a second step, we implement the affinity backup filter. Basically, this is a function that decides whether a node can be used as a backup for a particular partition or not. And the function has 2 parameters. So every time Ignite tries to assign nodes to a particular partition, it will first assign a primary node, just choose it randomly, and then we'll go one by one through all other nodes, and using this function, it will check whether this node can be a backup or not. So the first parameter here is the candidate node, the one that can become a backup. And the second parameter is the list of nodes that are already assigned. So the first one will be a primary node, and then you will have all the backup nodes that are also already assigned there. And what are we going to do is we simply will take the value of this attribute rack here from the candidate node, and then we'll do the same for the primary node. So the first one in the list is the primary node. We get the primary node here, and then we get the value for the attribute rack. And then we will compare the values, and we will return true only if these values are not the same, which basically means that we allow a node to be a backup only if it is running on a different rack from the primary node, right? So if a candidate rack is on the same rack where the primary node is, we return false. So we say no, we do not allow this candidate node to be a backup for this partition. And as a result, we will have that's the same picture, but distribution is different. So distribution of backup nodes is different here. And the difference is that basically we have all 4 partitions on every rack. So here we have A, B, C, D, and here we also have A, B, C, D. And even if we lose the whole rack in this case, we still have all 4 partitions. System is fully available, fully consistent. You have no downtime. You can restart the nodes. It will rebalance automatically. But you did not have any downtime. All right? So no partitions lost. So that's how you can approach, that's how you can solve these availability issues in this kind of deployments. This is very typical for cloud deployments with different availability zones, I think. All right. So far, I was talking about how we work with availability in a memory-only scenarios. But obviously, within memory-only scenarios, it's always possible that you lose some data. You can pretty much lose the whole cluster, for example, right? In this case, you lose all the data. You have to restart the cluster, reload the data, but you actually don't have a data source to reload from. So you kind of became unavailable forever. So what can you do with that? You can add persistence, right? So you can add a persistent storage that will save your data forever, and you will be able to reload from it. So that's the first option of persistence that is provided by Ignite is integration with any kind of third-party persistent storage. It can be relational database, it can be HDFS, MongoDB, Cassandra, whatever. But this approach has several disadvantages. So it works, right? So if you lose your cluster, you can restart it and you can reload the data. But if you have to reload the data, it means that the system becomes unavailable for a significant amount of time. Because if you have a large data set, it takes time to reload the data. In addition, especially if it's a single instance database like Oracle Server or something like that, this database, this persistent storage becomes a bottleneck, mainly for updates, because on the in-memory cluster level, all updates will be distributed. So clients will send updates to different nodes here, right, on Ignite level. But then all these Ignite nodes will propagate all these updates to a single database server, which creates a bottleneck and seriously affects the performance of updates on the cluster. And also, it's obviously a single point of failure, again, especially for single instance databases. Because if it fails, system also becomes unavailable. Whenever you update something, you want to update database as well. And it will not be updated until the database is back up. So basically, in this case, the availability of Ignite depends on the availability of the underlying persistent store. And to mitigate all these issues, all these disadvantages I just described, we came out with what we call memory-centric approach, which basically means that we still function primarily in memory. So processing is done in memory. The data is also in memory, but it also can be on disk. And it's based on this durable memory architecture, which is kind of similar to virtual memory architecture that you see in operating systems. The only main difference is that operating system use it for swapping. So when it runs out of RAM, it starts to write it on disk. In our case, disk always has all the data. So whenever you read something from Ignite, you can take the data from memory or from disk. And this will be completely transparent to the application. And so coming back to those disadvantages of the other approach that we had, so first of all, it allows you to do instantaneous results, right? So whenever you lose the cluster for whatever reason, you can just restart the nodes and continue using it. You don't have to reload the data. Because this storage is highly integrated with the ignited memory storage, and it's completely transparent for the application. The data location is completely transparent for the application. So you can execute SQL query, you can execute any kind of operation on the data in Ignite, and Ignite will automatically figure out whether the data is in memory or on disk, and will lazily fetch the data into memory if it's needed, right? And it's also distributed, so you have the portion of the data on each node on disk level as well. So it's a completely distributed disk storage that is added as another data storage layer under the memory layer, right? So you don't have a bottleneck on updates. Every node, every update happens locally on every node, right? It's not going to any single database server. And there is no single point of failure. So you can lose one node and you still have all the data available because all the backups are available on the disk level as well. All right, so that's how the Ignite network persistence works by itself. So this picture basically represents a single node. The storage is distributed, and every node will have several partition files, right? So here it's like from 1 to n, but actually it will be a subset of partitions on every node. And whenever we update something, we first update the memory. We first update the RAM. And then we synchronously update the write-ahead log. And that's the only thing that is updated synchronously. We do not update partition files synchronously with the cache update because that would be very slow. Write-ahead log update is much faster because it's a append-only file. And it's very fast. So the only thing we do synchronously with the update is we write to the end of the append-only write-ahead log file. There's no network communications. There are no random access like in the middle of partition files or anything like that. So it's a pretty fast operation. And then we acknowledge the client right away. And then there is a checkpointing process which happens in the background, which basically gets all the dirty pages in memory that are not persisted yet, and in the background saves them into disk. So this guarantees full consistency of the data because you can recover at any moment of time, having the latest snapshot of the partition files and the write-ahead log. So this combination gives you full consistency guarantee, as well as good performance of update operations. Okay, so everything that I talked about so far was available in Apache Ignite, open source community version. There are a couple of features I want to talk about, which are available only in GridGain Enterprise versions. And the first one is datacenter replication. So again, so far, we covered the in-memory only scenario, and we also covered persistence. But we were so far working like within a single cluster, right? What if you lose the whole cluster with all its data, including the on-disk data? Like you had a power outage in your data center and you lost all your servers for a significant amount of time. So you want to recover somehow anyway, right? And that's where the data center replication can help. So what it means is that basically you can have several clusters running, geographically distributed in different parts of the world even, right? And the data will be asynchronously replicated from one data cluster to another whenever you update it in the first data cluster, right? And if, like on this picture, if this data center 1 dies, for example, you can recover from this another data center here. Or you can even switch your applications and your clients to work with that data center. Sometimes it will bring like performance degradation, something like that, but the system will be available anyway, and it will give you consistent results. And that's what we're looking for. So replication allows to work in both active-passive and active mode. Active-passive means that you simply have an active cluster that gets update from clients, and passive cluster simply gets all this data through this replication channel, which is established between the data centers, and clients work only with the active cluster. And whenever active cluster fails, you can switch to the passive cluster because it already has all the data. You can also have active-active bidirectional replication as well, which basically means that updates happen on both sides and replicated both ways. This is a more complicated case and more challenging because you need to deal with conflict resolution, which is very like application and data model specific. But Ignite provides all the capabilities to do that, all the callbacks and even some out-of-the-box implementations for conflict resolution as well. There are also different techniques for split brain resolution, like for example, if you lose this channel, replication will obviously stop. And what will happen is that on sender side, we will accumulate all the updates in a special local disk storage so that it doesn't blow up the in-memory queue, in-memory batch queue that we have on the sender side as well, right? So it will not run out of memory, but it will still accumulate all the updates in the storage, and when the channel is back, or actually when the receiver data center is back, that's another similar scenario, right? The sender will push all this accumulated data into the passive cluster. Okay, that's yeah. And the last one, last but not least feature I'd like to talk about is the data snapshots and recovery. So this is kind of similar to database backups, right? We didn't use word backup here because we use it for different thing. But that's pretty much the similar thing. You can take a snapshot, the whole snapshot, cluster-wide snapshot of your data, and then recover from this snapshot. So it actually addresses multiple use cases. It's mostly for operational errors. Like so far, everything we covered was about Ignite recovering the data itself, right? So you were using Ignite features to make sure that you never lose the data. But what if there is something in the software, or maybe there is operational error, some human does an error and like removes the table, or corrupts the data, or whatever. So you still need to recover from that. Ignite can't you can't detect this situation as an invalid situation. It's a valid operation from Ignite standpoint, but it corrupts the data. And that's when data snapshots and data snapshot recovery can help. So you want to periodically create these snapshots, and then if anything bad happens, you just recover from the latest one. So we support both full and incremental snapshots. Full snapshot is it's a full snapshot of the data. An incremental snapshot is a delta snapshot from the latest full snapshot, right? So you will probably create a full snapshot every day, and then create an incremental snapshot every hour based on the latest full snapshot. Obviously, creating an incremental snapshot is much faster than creating the full snapshot. And we also have a management console for that, where you can create schedules and stuff like that. And I want to show you that. So I have a quick demo regarding the data snapshots and the management of the data snapshots. Okay. I don't really like the fonts here, unfortunately, but I'm not sure I can do anything with that. Can you see that? It's not going to be a lot of code, so I think it's fine. So basically, this is just my simple project. I already have a cluster running, a cluster of 2 nodes on my laptop, and that's the configuration file. Configuration file is very simple. I just want to go through main points here. So it's an Ignite configuration, and what I did here is I first of all enabled persistence. So that's how it's enabled. So if you want to use the persistent storage for your data, you just put this persistent store configuration bin. In this case, it will be started with all defaults, but there are, of course, multiple tweaks and configuration settings that you can modify to do fine-tuning. In addition, I also enable the snapshots as well. So this is the snapshot configuration. It's required for snapshot functionality to work. And by the way, snapshots work only with the persistent store enabled. So if you are in memory only scenario, or if you use integration with a third-party persistence, snapshots will not work. You need persistence to be enabled to work with the snapshots. So that's pretty much it that you need to do to work with the snapshots, to create snapshots and to recover from the snapshots. I also have a data model class. It's very, very simple. It's just an account class which has a name and a balance. And these query SQL field annotations here, I will just use them to visualize the data. I will use the web console to show what data we have in the cache. Okay, and the last one is just a small piece of code where I create the cache. Again, I create with all default parameters. I don't need to specify anything else on top of I already did. The only thing I do is set index types to enable SQL for this class, again, just for visualization purposes. Then I create a cache and just populate it with some random data. So let me run it real quick. It will take like several seconds, I think. All right, so this is done. We created a cache, we populated it, and now I will go to the web console. So this is our web console, and this is the main screen, the dashboard, the monitoring dashboard. So we just created the accounts cache, and it has 500 entries in there, so everything is correct. And now we will go to the queries tab. So this is the screen that allows you to run SQL queries or scan queries, and just to look through your data. And I will just execute a very simple query, which will get me 10 accounts with biggest balances. And we get something like that, right? So we have some numbers over there. So, and now I will go to the snapshot screen. And I don't have any snapshots yet. So the first thing I will do is I will create the full snapshot. I just go to this drop-down. I click Create Full Snapshot. And I click Confirm. So the snapshot is created. It appears in this table down here. It has an ID. It tells me that it's a full snapshot. And I also have the time when it was created. And on top of that, I can also create an incremental snapshot. It will create the incremental snapshot from the latest full snapshot that I have there. So, and it appears here in the same table. So we have a full snapshot here, and it will have all the incremental snapshots like attached to the full snapshot it belongs to. Okay, let's go back to the queries screen and do something bad with our data. Like imagine I just destroy all the money there and set all the balances to 0. It's pretty bad, right? Again, from Ignite and from GridGain standpoint, this is a completely valid operation. Anyone can go there and destroy all this data, right? Destroy the tables or do something like this. And if we execute this query again, we will get zeros. So how do we recover from this situation? Without snapshots, there is no way. But we have a snapshot just created. So we go back to the snapshot screen. Yeah, we select the snapshot. Yeah, like this. And we click Restore right here. I click Confirm. Tell me that snapshot was restored, which means that I have all the data back. And if I go back to the query screen and execute it once more, we'll see that we have all the data back. So regardless of the fact that I just manually corrupted all the data, I was able to restore it from the full snapshot I created before. All right, that's it for today. If you have any questions. Write-ahead log is on disk. It's not in memory. If that's what you're asking. Yeah, it's distributed, so each node has its own write-ahead log, but it's on disk. So my point is that write-ahead log is much faster. Write-ahead log update is much faster than updating a checkpoint file because it's a append-only file, right?
Do you come back to the client and say it is successful after making at least one replication, or that's something configurable?
Oh, it depends. Yeah, it's configurable. So you can either wait for the primary node only or for all the replicas in the cluster. Mm-hmm.
So is it the exact replica of the cache that what you are storing? Because I look at it, we started using this by the way.
Okay.
Using, I think it's very good feature. So, but one thing I was not really like behind the scene, I was really working that when you're really creating this image or a partition file on the disk, is it exact same replica of whatever you have in cache? Is it do you have a different partition scheme when you're doing this checkpoint?
Partition scheme is the same, but it can be a superset of the data. So you can have more data on disk than you have in memory. So at the very least, it's the same replica as you have in memory, but you can have more on disk.
One related question is that, I guess, let's say that you have a hybrid requirement. You want to make sure that some of the data, let's say we have 5 years, you want to make sure that money is 3,000 in memory, and the rest of
No, not really. So what we do is we use LRU eviction policy, so which basically you specify how much memory you want to use in RAM. And if you exceed this memory, you just start evicting from memory, which will leave the data only on disk. And you will have the data that you most frequently use. If you have like more complicated use case, then I have this, one of the approaches that you mentioned will work as well, with having 2 caches, and like you can have a cache like without persistence, not without persistence, but with kind of unlimited memory consumption, right, and everything else with limited memory consumption, and you will make, this way you will make sure that this one is never evicted.
I have one more question. So
Okay.
if I have serial updates, right, they are chained together, they're dependent on each other. So do you support rollback or certain like procedure type of semantics?
We support transactions, yes. Fully acid complaint, so you can create a transaction, you can do multiple updates within a transaction, and you can then commit it or roll back.
I see. Nice.
About native persistence, so you have right path which are kind of similar to Cassandra, but you didn't say anything about like some other stuff like compaction or ability to make changes like life cycles.
Yeah, so I'm not sure about compaction in particular. So we have like, we have automatic defragmentation built in into the persistent storage, which works both like on memory and on disk actually, because it defragments the data within the pages, right?
That's what Cassandra.
Yeah, I think, I mean, if you take a look at many systems, not only Cassandra, I think you will find a lot of similarities there, architecturally. So our unique approach is that we don't just have on-disk storage, right? We provide more like memory-centric approach, where the primary data processing and primary data storage is in memory storage, and disk storage is used for overflow and for providing better consistency of the data, and better availability as well, actually.
So do you do multi-node transactions?
Yes,
So you do the 2 bits commit across?
correct.
In the cloud, of course, nodes come and go. Also, disk is not so simple. Dominant containers, et cetera, can block down as well. So, can you take snapshots to some other store, like to Mongo? So, in other words, take a snapshot, drop it to Mongo, and then restore from Mongo. Because restoring a cluster that's gone bad, it's already bad, so you might start a new cluster and restore it.
You can use the same snapshot functionality because you're going to restore it on another cluster as well. So there is actually no requirement to restore it on this particular cluster. That's actually, that's one of the use cases for snapshot functionality as well.
Cluster's gone bad.
Yeah.
Cluster's ill.
Mm-hmm.
Now you've got, it's got your snapshots in it, so how do you restore from something that's ill?
Well, snapshots are typically created periodically. So this web console also allows you to create a schedule for a snapshot, for snapshotting. So it will just periodically take a snapshot and you can recover from the latest one. So,
Snapshotting is really on S3 or somewhere else. It's not in the same cluster. The snapshot that you're taking is on a different, completely different cluster, or maybe on, imagine in AWS is on S3. Right?
yeah, it can be same cluster, it can be different
Or you can
cluster.
configure it
Yeah, you can configure to save the snapshot like anywhere.
S3, right?
Yeah, I think so.
Does the cluster, does the snapshotting feature support snapshotting to say S3? You have to do it to like a local provider.
Say it again. Sorry.
Can you snapshot to S3 directly?
S3 like
S3 buckets.
AWS S3.
Yeah, I think so. I don't see any restrictions here. Yeah, I mean, you can just point a location where you save the snapshot and then you can recover from there.
And it would look like a single entity in S3.
Yeah.
How do you deal with the data updates when you are in the process of
Oh, that's a difficult question. So yeah, I mean, there is a message sent across the nodes. So they're like on discovery level, they're organized as a ring. It's kind of a token ring architecture, right? So we have this message going across the ring, and it kind of, I mean, this is really like an implementation detail, but it does not block for a whole time of taking the snapshot. So it kind of, so it's,
When you're taking a snapshot on the node, you see update data in there.
yes, you can, yeah.
And what kind of data will be saved in the snapshot? And before my update or after my update?
Well, I mean, it's a race condition, right? So you can have it, or, I mean, if you have an update concurrent with a snapshot creation, you can end up having this update in this snapshot, or not having this update in this snapshot. But if you're not having update this in this snapshot, you will have it in the next snapshot, right? That's guaranteed.
My concern is that if I make multiple updates on the node, not in a transaction, and then the snapshot might contain partial of my updates.
No, it can, so if you have a transaction, then it will not happen.
Multiple updates, then it is possible that the snapshot might contain some of my batch of updates, right?
So again, so if it's a batch, what do you mean by batch of updates? I mean, the answer is yes. If it's not a transactional batch of updates, if a single transaction, then it's not possible. Because, I mean, it synchronizes with transactions as well. So if it's just a batch of individual updates, then yes, because they do not depend on each other in any way. No. No, that's not how it's supposed to work, of course. So once you create the cache, so maybe you destroy the cache for some reason when you exit the client. But yeah, of course, I mean, if you just create a cache and pop.
The fact of client connected or disconnected from the grid shouldn't affect the grid if everything done.
No, no, of course not. No.
Snapshots can be made to run additional code. For example, Kafka says that match it, what you where you're at, and then back when the overall offsets are.
No, not what I'm aware of. At least I think no. I think the answer is no. Yeah. When you restore, you mean? I think no. It's just it's our like proprietary mechanism, which it basically snapshots from the disk storage, not even from the in-memory storage. So you just take these files in proper way, like combining them with the write-ahead log and stuff, and saves them in an external storage, and then you can just recover from them.
Can you trigger snapshots from an API rather than console?
Yes, you can.
Are there any like significant improvements that you talked about that you're working on the GridGain?
Yes, probably the major improvements are all around SQL support, right? So we are kind of leaning towards being a SQL database. So the closest one is full transactional support for SQL language. So currently we have transactional support for key value APIs when you like do put and gets on the key value on the Ignite Cache API, right? If you do SQL, it's not enlisted in transactions right now. That's what we're going to have, I hope, by the end of the year. Yeah, that's probably the biggest one coming. And most of other improvements will be probably around SQL, better SQL support, and everything around that. Right, I think we're ran out of time. Thanks, everyone.